Hi and welcome to video 5 on integration for Unit 4, Topic 1 of the Specialist Mathematics curriculum. So we're going to look at integration by substitution today, and it'll probably stretch across a couple of videos, and this of course on the series is video 5. So have a look, there's the learning goal success criteria. Pause it if you need to have a look at this. Let's start by doing just a nice chain rule question. Calculate d dx of e to the 2x squared. This, of course, you'll know that when you derive an exponential function, you get the exponential function 2x squared. You have to multiply by the derivative of the inside function, which is 2x squared, and that's equal to 4x e to the 2x squared. So the next question is integrate 12x e to the 2x squared. When I do this integration, I'm actually going to separate this up so it looks like this, and that will give me 3 times the integral of 4x e to the 2x squared dx, which of course is 3 times e to the 2x squared plus c. So that's fairly easy, and that's what the mathematical method style questions look like. You're given something to derive and then asked to integrate something that links with the derivative you originally did. That's not always the case in specialists though, and you need a way of being able to integrate this without first knowing this. And there's a very logical process to it, so you may already in a position to work it out, but there is also some methods to help you. So let's have a look at integration by substitution. And there's multiple ways of doing this. I've set out first of all my way, then I've set out the textbook way, and then there's other ways, so you choose what works for you, but I quite like this method. So we start with our integral here, and in our integral we have a big component, a main function I'm calling it, and a small component which probably looks like du dx or something quite similar. Hopefully it's a linear factor of du dx, where u is the inside function of the big component. So you're probably going to have something that looks like, if you cast your mind back to the calculus differentiation rules, it's probably going to look like a product rule, because you should have, and look for this, you should have f dash of x times by f of x. For substitution work, you should have that. So if you do have that and you can spot it, get your main function and select u to be the inside component of that main function. I've selected u in this case to be 2x squared. And that gives me, and this is the next part of the process, it gives me du dx equals 4x, which means that du equals 4x dx, and that means that dx is equal to du over 4x. So what I'm going to do is I'm going to take this dx and I'm going to work out what it's equal to in terms of du and do that substitution. So as I come back across to here, step 3 is to sub my dx in. So I'll swap dx for du over 4x. The 4x cancels with the 12x to leave me 3, and I've got e to the u. So now I'm integrating e to the u, 3e to the u with respect to u, which is an easy integral because that's just 3e to the u plus c, and now I can substitute in that 2x squared for my u. Smiley face. If I go back up to the original question, it was the same question, and you'll see that the answer here is the same as the answer there. So we're very happy with that. Textbook method's very valid as well. It's quite similar. It's basically the same thing, but they just set it out slightly differently. If you're integrating this, then again choose your appropriate u. U equals 2x squared. Then f of u equals e to the u. That's your original function. And du dx equals 4x. So then they say, well, let's swap e to the 2x squared out for e to the u. And then we're left with 4x dx. And we know that 4x is our magic key, which is why we have that there. And we put the other number at the front. And then we swap 4x for du dx, cancelling out the dx's. And then we end up with this. I just find that sometimes people find it a bit harder to find the 4x using this method, but you choose. Let's have a look at an example, and I'm going to do them my way, I'm afraid. So in this first example, I can see that cos is the main function, and this is going to be my u. And this, I'm hoping, will be f dash of u. So it should cancel out when I do the overall derivative. So, the integration. Oh, and when I substitute the derivative in. a is equal to the integral of 2x squared minus 1 cos 8x cubed minus 12x dx. I'm going to first of all let u equal the inside function 8x cubed minus 12x, and that means that du dx is equal to 24x squared minus 12, which means that du is equal to 24x squared minus 12 times dx, and therefore dx is equal to du over 24x squared minus 12. So there's my rearrangement and calculation there. I've got a dx and I've got a dx. I'm going to do that taking it out, but also I've got a u, and I've got what u is equal to. So this is now equal to the integral of 2x squared minus 1 cos of u times by du over 24x squared minus 12. And so of course, and I will need a little bit more space, particularly since I've got a second question, this will be equal to the integral of 2x squared minus 1 over 24x squared minus 12 cos u du. Now if you get to this point and you're like, well, where do I go from here? Always expect the x's to cancel out. If it's a substitution question, this should happen. So now I'm looking for that opportunity. 2x squared minus 1 over 12 times 2x squared minus 1 cos u du, and of course we now get that cancelling out, leaving us with 1 over 12 times the integral of cos u du, and that's just equal to 1 over 12 sine u plus c, and of course that's equal to 1 over 12 sine, we substituted u out for 8x cubed minus 12x, don't ever forget to do this final step, 12x plus c. So there's part A, and it's about being a little bit clever, but this is step 1, this is my step 2, and this is my step 3, and the rest is cleaning up. You just have to be careful that you recognise that 24x squared minus 12 can be factorised, allowing that cancelling out to happen. So there's A, and part B looks like this. So I'm going to bring part B over to the side here, and I might even grab a copy of it to do that, to facilitate me being a bit lazy about it. Okay. So again, this looks to me like the bottom function is my main function, and my u is inside there. So that's my u there, and this is my, hopefully, u dash variant, or f dash of x. So that's what I'm aiming towards, and when I integrate this, I'm expecting to get a log. So start getting used to what you expect to get. So I'm going to start by saying let u equal the inside function x squared plus 1 of the major function x squared plus 1 to the power of 7. And then du dx is just equal to 2x, which means that dx is equal to du over 2x. That's a rearrangement in one step. And I'm going to bring that back to here. And this becomes the integral of 6x over u to the power of 7 times by dx, which becomes du over 2x. Now the x's cancel out, the 2 and the 6 cancel out, leaving just a 3, and this becomes 3 over u to the power of 7 du. Now this is going to be quite easy from here, but I actually said earlier I was expecting to get a log because I had that 1 over. I'm not actually going to get a log, so I misspoke there, but it's still definitely worthwhile having an idea in your head what you expect to get. So I can write this as a negative power, which of course means that I now get 3 u to the power of negative 6, so I raise it by 1, divide by negative 6, and I add a c to that. Now I just got to do that substitution back out. So 3 over 6 is negative a half, and actually, well, I'll do the substitution out. U is x squared plus 1, x squared plus 1 to the power of negative 6, but I might put that back together as one fraction, 1 over 2 x squared plus 1 to the power 6. So I'll put that negative 6 and change the power to be in the denominator. And of course, I've almost forgotten to finish off with a plus c the whole way down. So don't forget that with an integration. So there's our integrals for part A and part B, both using substitution, both slightly trickier, but I wanted you to see a couple of hard examples. And that's example 1. All the best.